Welcome. In this lecture, we will discuss three topics basically: ladle desulphurization using synthetic slag, alloying, and the stainless steel making. So, concept covered is ladle desulphurization using synthetic slag. This will be discussed, and effective deoxidation and alloying by cast technique, and stainless steel making using EAF AOD method. That is the electrical furnace and argon oxygen decarburization. Okay, desulphurization of the synthetic slag first. Let us. So, as the name suggests, synthetic slag, basically we artificially prepare the slag. That is, we add the constituents, basically CO and the aluminum we add to make it a highly reducing and basic slag. And then by gas stirring, we increase the kinetics. Okay. So, that is the synthetic slag treatment in the ladle. Okay. So, after you prepare the steel, as you know, that is the sulfur can only be controlled under the blast furnace operation, because there also we have a basic slag and reducing slag. After that, in steel making, you do not have much control. Actually, effectively, we cannot reduce any amount of sulfur. So, sometimes before to reduce the load of the blast furnace, sometimes we don't do much of some of the sulfurization is carried out in between the blast furnace and the LD process. That is called the external desulfurization. So, this to some extent reduce the load of the blast furnace. Okay. And finally, if you want to reduce the sulfur, so sulfur can be reduced to 0.05 level, and then if I want to reduce it to 0.01 level, that is 100 ppm of that level, then we can do it by synthetic slag treatment in the ladle. Just after the steel is prepared into the basic oxygen furnace, that is LD, and then when it is tapped into the ladle in the secondary steel making, in the ladle itself, we can treat that steel with synthetic slag, and we can reduce the sulfur content quite low level, that is 100 ppm. And if you want to further reduce the sulfur content to a very of the order of 10 ppm like that, in that case we require some injection technology. There is a calcium powder is injected, that we will talk about later on. Here basically we will talk about the synthetic slag treatment of liquid steel in ladle, and that can also reduce the sulfur content to a very low level of the order of 100 ppm, even lower. So, now what is the thermodynamics? Let us see. Basically, as I said, ladle desulfurization is achieved by adding aluminum and calcium oxide. Aluminum is added to deoxidize the bath such that the dissolved oxygen in the bath is very low, condition become reducing, and calcium oxide is added to make the basic slag. So, both this basic and reducing condition favors the desulfurization, as you all of you know. And under this condition, the final reaction become like this: calcium oxide and the dissolved aluminum in the bath and sulfur. This reaction forming calcium sulfide and alumina. Okay, so this is the final reaction you can consider in ladle. So, this is the equilibrium constant. You can write, that is the activity of the product divided by the activity of the reactant. You can write in this way, and you can note that is all the activity in the slag, all the constituents in the slag, we have represent their activity in terms of Raoultian standard state, that is pure solid at the standard state. And for the dissolved constituents like aluminum and sulfur, we have used Hendian standard state, that is the 1 weight % standard state we have used to express their activity, and accordingly K has been calculated, and K is like this. Okay. And then you can simply from here, that is the activity of calcium sulfide, you can represent in terms of weight % of sulfur, because activity of calcium sulfide, or you can say weight % of sulfur into the liquid steel is directly proportional to the activity of calcium sulfide. So, we can write this thing, there is the activity of calcium sulfide, we can write in terms of weight % of sulfur into the bath divided by this thing, that is the HS, we can directly like as WS, considering the Hendy's law is valid up to 100%, or Hendian activity coefficient, that is the WS, and then multiplied by Fs, that is the Hendian activity coefficient also we can calculate. But thing is that Hs is directly proportional to the Ws, right. So, that is why we can write this way, and that is why I have written this is called the partition coefficient. This is called the equilibrium partition coefficient of sulfur, that is the weight % of sulfur divided by weight % of sulfur in the slag phase divided by the weight % of sulfur in the metal phase under equilibrium condition is called the partitioning. there is a partition coefficient under equilibrium condition, and we have represented it as LSE, and that is directly proportional to, that is the K to the power 1/3 activity of CO and weight percent of aluminum to the power 2/3 and activity of L2O3 to the power 1/3 in the denominator. So this thing we can find, that is the, obviously we can find that LSE is directly proportional to K to the power 1/3, and as you can find, K is again inversely proportional to temperature. So if you increase the temperature, the reaction, that is the partition coefficient, will decrease. So at low temperature, partitioning will be better, sulfur partitioning will be better at low temperature. And you can see there is the, as more the activity of CO, your partitioning will be high. If the dissolved aluminum in the bath is high, your partitioning will also be high, and only if the activity of L2O3 has to be low into the slag, that will favor the higher partitioning. So sulfur partitioning, so you can see that LS versus weight percent of, that is the weight percent of CO in this x direction and the partition coefficient in the y direction. As what you can find, as you increase the CO, your partition coefficient increases, and obviously if you increase the weight percent of aluminum in the bath also, then also partition coefficient increases. So increase in percentage of CO and percentage of aluminum increases the partition coefficient of sulfur. Now let us make some calculation to understand, that is the, what should be actually the partition, equilibrium partition coefficient, how much the equilibrium partition coefficient is required for an effective desulphurization. Suppose we want to reduce the sulfur from 100 ppm, 100 ppm means 0.01 weight percent to 20 ppm, right. As I said, by synthetic slag treatment we can easily make it to 20 ppm, 200 ppm, even that is the 20 ppm, 0.002%, okay, very low. Assume that is the mass of the steel is 150 tons and that of the slag is 2 tons, right. So then sulfur to be transferred to the slag, how much sulfur has to be transferred is around 0.012 ton, because you are reducing the sulfur contents from 0.01 to 0.002, and weight is 150, that is the weight of the mass of the steel is 150. So simply 0.012 tons of sulfur has to be transported from liquid metal to the slag phase if you want to reduce the sulfur from 100 ppm to 20 ppm, right. So 0.012 ton or 12 kg of sulfur has to be transferred from metal to the slag. Now, so the weight percent, in that case, weight percent of sulfur in the slag will be how much? That is the, this much of sulfur has joined, 0.012, and out of 2 ton it is around 0.6 weight percent, okay. So in 2 ton of slag you will transfer 12 kg of sulfur from metal to the slag, and then the weight percent of sulfur in the slag will be simply 0.6 weight percent. And then, so the LS become what? That is the 0.6 weight percent in the slag phase, that is the weight percent of sulfur in the slag divided by weight percent of sulfur in the metal. So divide, that gives you, that is the partition coefficient has to be 300, okay. So now this is the partition coefficient that is required to be exist into the industrial plant, any industrial plant, so or vessel, right. So LS has to be 300. Now you can understand that is the, it is very difficult to attain the equilibrium in the steel making, in the ladle. Equilibrium attaining is quite impossible, but still we have a gas stirring, that is the mixing is fast, that happens, that brings the ladle closer to the equilibrium, but it is further away because you cannot mix it. That is, for that case it has to be an ideal reactor like CSTR, continuous stir reactor. If it is completely mixed, that means instantaneously mixed, so mass transfer does not have any role to play. But in this case, in any real reactor, the mass transfer definitely, because all the processes are that is the high temperature process, so chemical kinetics does not play much role, but mass transfer plays a role. That is the transfer of the pieces from the bulk to the reaction interface is very important. Now that thing, that is if you want to, but by gas stirring you cannot ensure that it will be, you can be completely, it will be a CSTR. It will not be a continuous stir reactor where it is an ideal reactor. CSTR is an ideal reactor, you may be knowing that, and in that case what happens, if you give some tracer instantaneously everywhere, becomes the average concentration, instantaneously mixed up, that is the kinetics does not have any limitation. But in any real reactor, it is not the situation. You cannot have a ideal CSTR type situation. So thing is that here, that is the impurity has to be transported, some resistance will be still be there. Okay. So because of that, you cannot, it is unlikely to assume that is the equilibrium will be there. So if it is not, equilibrium is not achieved, then if you want to get this much of partitioning 300, so equilibrium partitioning has to be much greater than this. Basically it is not attaining. Okay, so it will be greater than this. So since equilibrium is not likely to attain, that is the equilibrium partition coefficient should be greater than 300 obviously. 300 is your partition coefficient. At time you measure to take two samples from slag and the metal and then see it is that is the weight percent of sulfur on the slag to that of the metal is 300. That has to be there under certain condition. If you want to reduce the sulfur from 100 to 200 ppm in the metal, then the partition coefficient has to be that. But the process does not attain the equilibrium. That is why equilibrium partition coefficient could be much higher. So it has been found, that is the plant trial has shown that to have the effective desulphurization, that is the LAC, should be of the order of 100 and above, 1000 and above, not only 300, 1000 and above has to be there. That is the equilibrium partitioning. Then only you can attain this type of, that is the actual partition coefficient of 300. That is the weight percent of sulfur in the metal to that of the weight percent of sulfur in the slag to that of metal under industrial condition, not under equilibrium condition. So if you want to attain 300, then equilibrium partition coefficient has to be high because the process does not attain the equilibrium. So, and that this high value, that is the 1000, that is the LAC of the order of 1000, if you want to achieve it, then obviously you should have a very high calcium in the bath, and it has been found that is the slag has to be, that is the calcium oxide has to be, that is the calcium oxide in the slag has to be saturated. It should be very almost saturation condition. That means the slag should be saturated with CO, means this activity should be of the order of 1. That is the maximum activity that you can achieve in the slag. Okay. So if it is 1, then your partition coefficient, equilibrium partition coefficient would be very high. Okay. And then you can achieve this type of this much of lowering of sulfur. So that is why you have to improve the kinetics of the process by which the desulphurization kinetics has to improve such that it become very close to the equilibrium. Then if it is close to the equilibrium, then think is that you can get 1000 that is that thing also, that is the equilibrium partitioning, that is the partitioning of sulfur slag to the metal will be very close to the LAC value. That means it can be of the order of 1000, right. So your too much of partitioning you can accept. So in this slide we will discuss the kinetics of desulphurization, and we will consider that is the desulphurization follows a first order kinetics, and usually it is the case. So the first order kinetics you can like this, that is the on the left hand side, that is the dWs dt, that is the rate of change of concentration of sulfur in the metal, that will be equal to Ks into Ws minus Ws equilibrium, where Ks is the first order rate constant, Ws is the concentration at any time in the bath, and Ws equilibrium is the equilibrium concentration in the bath. Okay. And obviously it is a mass balance statement you can find, that is, this is the rate expression, that is the rate at which the sulfur is transferring from metal to the slag phase. As a result, there is a depletion of sulfur into the bath, that is on the left hand side. Okay, this is simply a mass balance equation based on first order kinetics. And Ws equilibrium again you can write in the form of, that is the weight percent of sulfur into the slag phase. That is why slag phase is defined by first bracket and the metal phase is defined by the third bracket. Okay. So concentration of sulfur into the slag phase divided by the partitioning coefficient, equilibrium partition coefficient, right, because that is the definition of equilibrium partition coefficient, that is the LACQ is Ws by Ws equilibrium here in this case. So So, this is basically Ws is the concentration into the slag phase, and corresponding equilibrium concentration into the metal phase can be given by Ws by Ls Eq, right. So, this reaction will continue as long as Ws reach the corresponding equilibrium concentration into the metal phase to that of the concentration in the slag phase at a particular time, right. So, this is the definition. Now, Ks is called the first order rate constant, and it has a unit of 1 per second, and it can be correlated with the mass transfer coefficient and the specific interfacial area at the reaction interface. Where Km is the mass transfer coefficient, it has a unit of centimeter per second, and specific interfacial area you can write that centimeter square per centimeter cube per unit volume. So, if you take a product of these two, you will get per second. So, there is Ks, there is a rate constant is correlated with the mass transfer coefficient and the specific interfacial area at the reaction interface. And the integral form, if you just integrate this equation with respect to time, then you will get this form, that is ln of Ws naught minus Ws equilibrium divided by Ws final minus Ws equilibrium is equal to Ks into T. Okay, just you have to integrate, and keeping in mind that on the left hand side you have a minus sign. So, if you integrate it, you will get this form. Okay. So, this is the integral form of first order kinetics. Okay. So, obviously, you can calculate WSF if you know initial concentration of sulfur in the bath. Also, if you know the equilibrium concentration, what will be the equilibrium concentration in the bath, and Ks is the rate constant, there is the per unit time, there is the per second, and T is the total time. Okay, what is the time after this much time? So, time and Ws, these are, if you know any one of them, then you can calculate the other. Okay. So, if you want to calculate the sulfur concentration after say 15 minutes, so you know T is equal to 15 minutes, what will be the sulfur concentration in the bath, you can calculate. Okay. So, that is the thing. So, using this equation, you can calculate the final concentration of sulfur in the bath, or you can calculate to get a certain sulfur concentration in the bath, what will be the time required. Okay. So, this is the utility of the kinetics. So, next, the correlation of rate parameters with the flow rates. Let us see, this is the thing, that is the Ka, that is the rate constant per second I have plotted versus the flow rate of gas from the bottom, and as you can find, with increase in the flow rate, gas flow rate, your mass transfer coefficient increases, the rate constant increases, right. It is proportional to their Q to the power of 0.25 initially, and then beyond a certain gas velocity, what you can find, then there is a steep rise in the value of rate constant. Suddenly there is a steep rise. Okay. And so, these basically indicate that is the rate constant is increasing. How the rate constant suddenly increase? Either it can increase the mass transfer coefficient or the specific surface area, or both. Obviously, the mass transfer coefficient can increase in the concentration boundary layer. Mass transfer coefficient can increase depending on the hydrodynamic condition, fluid dynamic condition across in the concentration boundary layer. And when the concentration boundary layer become turbulent, then mass transfer coefficient also increases significantly. Okay. But this steep rise in increase, it is not only due to mass transfer coefficient, it is also due to the specific surface area increment. And cold model simulation has showed that when you do such experiment, basically cold model simulation is done with some cold low temperature analog, like steel is represented by water and slag is represented by some mineral oil. And then it has been found that beyond a certain velocity, the slag get emulsified into the metal phase, and that increases the specific surface area tremendously, and that is basically the reason why the rate constant suddenly increase very steep. It's very, you can see the slope is very, so it suddenly increases very high because of slag emulsification. Mass transfer coefficient increases, but it doesn't give so much of increase. It's basically increases because of specific surface area increment. So, That is, the data in the figure are taken from a pilot scale gas star ladle desulphurization. It is this data you can find. This is from the pilot scale gas star ladle. And two distinct lines with different slope fitted by the data that we have just discussed. And beyond the critical velocity, rate constant increases tremendously. And as I said, this attributes mainly because of emulsification of the slag in the metal. It is attributed to the extensive slag emulsification in the metal phase as indicated by laboratory cold model experiments. That is the thing I said. That is, it is the specific surface area increases and the kinetics become very fast. And under this condition, you can consider that is the process will be closer to the equilibrium condition. Okay. So then the LS and LSE will be very close together. Okay. So a high that is the then you can achieve a very high partitioning in that case. You can collect it together. So that's why this is the synthetic slag treatment. In synthetic slag treatment, what I said, you have to use aluminum to deoxidize the bath and the lime powder to make the slag basic and aluminum to make the slag reducing. That is very good condition for desulfurization. Thermodynamics is up to this. And after that, you have to improve the kinetics. Unless you improve the kinetics, you cannot achieve a very low level of sulfur. And that's why if you want to improve the kinetics, it has been found beyond the critical gas velocity, you have to start the bath. So for desulfurization, you require a very strong stirring of the bath beyond a certain critical gas velocity or volumetric flow rate of the gas. Okay, so these values are given. Okay, thank you. We will go to the next topic, that is the cash. Cash is basically called the composition adjustment by seal argon bubbling, and it was invented by Nippon Steel Corporation in Japan, and for increasing the yield of deoxidizer and the alloying by restricting with the restricting interaction with the overlapping slag and the atmosphere. Okay. So what basically does is that in the ladle you just do the alloying and the deoxidizer, but you do some modification. What modification? You just insert and snorkel, high alumina refractory lined snorkel you just insert in the slag eye, such that the slag eye get detached with the your slag as well as atmosphere. Okay. So that is the thing, a high alumina snorkel, high alumina means high alumina refractory lined snorkel is introduced through the slag eye, and alloying elements are added through the snorkel during the argon purging. You are doing the argon purging, then you add the alloying element as well as deoxidizer. So what happens, what is the advantage is that in that case, whatever you add the deoxidizer or the alloying element, they do not interact. You can minimize the interaction with the slag as well as open atmosphere. That is the major advantage. As a result, both the yield of deoxidizer as well as alloying elements increases, because these deoxidizer and alloying element do not unnecessarily react with the slag as well as atmosphere, reducing their yield. That basically reduces their yield. Oh, that is the advantage. And intense stirring also you can ensure, because it does not matter now if you basically we do not make very intense stirring from the point of view, because I want to remove or reduce the slag eye as low as possible, because the greater the slag eye, greater is the interaction, okay, with the atmosphere. And so under this condition, when I dip the snorkel just over the slag eye, so if you just increase the gas velocity, that problem is not there, because it is not exposed to the atmosphere, or also the slag will not be able to come into the snorkel. So that advantage is there. So intense stirring is possible, and because of intense stirring, you can melt the alloying elements and you can enhance the kinetics improved. So otherwise, basically without this top snorkel, you cannot start the bath intensely. That is the disadvantage. So if you use the snorkel, then you can start the bath in a very intense way. That is very intense stirring is very good from kinetics point of view as well as for alloy dissolution point of view also. So intense stirring enhances the mixing, there is the melting and the mixing, and no interaction with the slag and atmosphere enhance the yield. And heat compensation could be done by the oxygen blowing also. There is an option for CAS OB process, oxygen blowing from the top. You can add some aluminum and then you can add some oxygen, and then you can oxidize the aluminum, and then you can generate a lot of heats. Obviously, you can think that in that case the impurity will be, you are generating some impurity, but because of intense stirring, basically it is supposed to be the inclusion gets separated. Okay, so this is basically the cash system. If you can see, this is a very simple equipment and operation. As a result, you have low running cost and investment, quick treatment, and low temperature drop, because simple equipment you can find. And then alloy addition under argon atmosphere, because your argon is there here, the atmosphere is completely argon because no interaction with the atmosphere. Okay, so alloy addition, so low reoxidation, so alloy doesn't reoxidized because you don't have interaction with the atmosphere. Also the slag is separated, slag is off from here. So that's why the low reoxidation, high yield, and precise composition adjustment. You can precisely composition adjustment is possible. And you can see slag off, slag is not there inside, because when the slag eye forms, you just dip the snorkel. As a result, there was there's no slag entrapment into this region. Okay, the slag off. Basically, it also gives this thing, low deoxidation, high yield, and the precise composition control. Argon stirring in the snorkel, effective removal of oxide, that is the thing. Because since you have good stirring, basically stirring also help in removing the impurities. So since you have a good stirring, that is the whatever the alumina form, they are supposed to float on the top of the liquid bath. Okay, so then you can separate it out. That is the thing, and no disturbance of the slag layer and quick homogeneity. These are the things. And all the oxygen blowing into the snorkel, raising the temperature of the steel. And obviously you are introducing some amount of alumina, but because of good stirring, those alumina particles will float up at the top of the metal bath. It is expected. And then you can take it off and then completely slag, take out the slag. So this is developed at Nippon Steel, this process. So if you do the alloying under this argon atmosphere, then obviously the yield will become high. So now the principles of stainless steel making, that is also very important. That is the using the electric arc furnace and argon oxygen decarburization. And there is the high, what you do basically, first you make a melt, high carbon chromium nickel melt you make in an electric arc furnace. You just melt the scrap, and then high carbon ferrochrome, chromite ore, and the nickel alloying addition also. After doing that, you make a melt in the electric arc furnace. You can easily do that. You can melt it under the arc. So you can first make a high carbon chromium nickel melt in the electric arc furnace, then it is transferred to the AOD, argon oxygen decarburization. Now think is that what is the advantage of argon oxygen decarburization? What is the role of argon there? Argon basically dilutes the CO gas, that is the advantage. During decarburization, CO is evolving, so you can dilute the CO gas by argon. As a result, the partial pressure of CO will decrease, and if partial pressure of CO is decreased, then decarburization will move in the forward direction, and you can carry out the preferential removal of carbon over chromium. Because if you oxidize the bath, there is a high carbon chromium nickel bath, if you give the oxygen, argon oxygen, if obviously you are supplying oxygen. So when you are supplying the oxygen to oxidize the carbon, chromium and nickel will also oxidize. But our idea is to do that. I want to preferentially oxidize the carbon, leaving the chromium and nickel in the bath. That is my intention. So because I want to keep, finally I want to keep the chromium and nickel in the bath, but I don't want the carbon in the bath. That's why I want to preferentially remove the carbon over nickel and chromium. And that can be done if I can reduce the partial pressure of CO, because the product of oxidation of carbon is a gas, CO gas. All are solid oxide, the chromium oxide, nickel oxide, all are solid. They will remain into the slag, but CO will go away from the system. So the CO formation is definitely controlled by the pressure. Okay, if I can reduce the partial pressure of CO, I can preferably move the decarburization reaction. Because other reaction, because Cr2O3, there is the oxides, they will not be influenced by the pressure. So since the oxidation product of carbon is gas, so it will be influenced by the your pressure. So if I reduce the partial pressure of CO, I can preferentially so move the reaction, okay, over chromium and nickel. So argon in the AOD dilutes CO, reduces partial pressure, and carbon can be preferentially removed over chromium at another thing is that that is the thing. So basically by reducing the partial pressure, you can carry out you can remove carbon in preference to chromium and nickel. But again, there is the carbon oxidation can be preferentially removed over chromium at high temperature also. That is also possible, because as the temperature increases, I have shown you into the EF when I was teaching the electric arc furnace steelmaking by rustless process. We have shown that is with increase in temperature, chromium oxide become much less stable compared to the CO gas, because CO gas moved in this direction. There is the CO in the Ellingham diagram. If you see, this is CO line goes like this, and chromium oxide line is this Cr2O3, and this is your C2CO. So this line, so at higher temperature, if you go, this is basically delta G naught versus time, as you know, temperature. So you can find at this temperature, this is much stable compared to this. So basically, if your temperature is high, around 1800 degrees centigrade, maybe 1800 degrees centigrade, okay, at very high temperature, okay, at very high temperature, your CO is more stable compared to chromium oxide. So you can preferentially remove the carbon over chromium at high temperature. That is done. If I am to produce a stainless steel in the electric arc furnace, I have to do that. I have to increase the temperature very high, and then I can preferentially remove the carbon over chromium. But the problem is that at high temperature, there is a huge refractory load on the refractory, because refractory erosion, corrosion will be very high. So refractory life will be high. So high temperature operation is not desirable. Even that, when you increase the temperature of the steel so high, and after that you have to cool it. So in that case, you have to use some coolant or like this. So that becomes a cumbersome process. So instead of making the stainless steel in the electric arc furnace, after you make the melt, you transfer it to a AOD vessel, and under low pressure, you can carry out this preferential oxidation of carbon over chromium even at very low temperature, because then temperature is not requirement when you dealing with the pressure. Yeah. So you can see that is also see the final reaction. You can write like this. You can write chromium oxide, carbon reacting with the chrome. There is the CO plus Cr. Okay, you can write like this. This reaction will be go in preference, and then you can write that is the weight percent. This is the thing. That is the log of weight percent of chromium in the bath divided by the weight percent of carbon in the bath. That is the relative amount of chromium to carbon in the bath. That will depends on these things. This is a very important ratio, because I want to increase this ratio as much as possible, very high value. So if I want to have a high value, you can find that in that case temperature has to be high. If temperature is high, this value is low. So this value is going to be high, Cr2a, because it is only the positive number, this will be a negative number. So lesser the negative number, bigger will be this value. So at high temperature, you can improve this, you can improve the ratio, and also at low partial pressure of CO, you can also improve this. Lower this value, bigger, there is the 8.7 only 8.76 is positive number, these are the negative numbers. So negative numbers, if the negative numbers is less, then this value will be high. Okay. So that can be done if temperature is very high or PCO is very low. So that's the thing. So carbon can preferentially remove lower chromium at high temperature. At low partial pressure of carbon monoxide, the same can be achieved even at lower temperature. That is the thing. So at lower temperature also you can achieve it. After carbon has been lowered to the desirable, say 500 ppm, you can add some ferrosilicon and to recover the chromium, because some amount of chromium will get oxidized whatever you do partial pressure reduction, but some oxidation will take place, chromium will go into the slag, but you can take back those chromium also by using the ferrosilicon, okay, and which has been oxidized. Okay, so this is basically the principle. One thing is that this reaction can be moved in the forward direction, that is basically, and under condition of high temperature or very low pressure. So if you high temperature is not good thing, because it increases the load of the refractory. So load on the refractory, so it is better to reduce the partial pressure. That's why I am telling you just transfer it to the AOD vessel, where argon as a diluent, it dilutes the CO and reduces the partial pressure of CO, and that basically increases this ratio significantly. Okay. Now let us see the stainless steel making, now the industrial process, what is there. Some of the points I will write that is used in the industry. This is the EOD vessel that looks like. This is the looks like EOD vessel. You can find there is the oxygen is injected through a supersonic lens, just like in the oxygen steel making in the LD process. Okay, is a supersonic oxygen lens is there, and you can find also a side lens. Through the side lens, basically argon as well as oxygen is purged through it. Okay. And about so this AOD process, because you don't have to use the vacuum, that is the advantage, and it also, that's why cost wise also it is less. So about 70% of the world's stainless steel production is done by the EAF-AOD process, this process. Okay. And initially the oxygen is purged from the trough. Initially means when you start the process, when the carbon in the bath is very high, in that case you just start the oxygen from the top, such that you can emulsify the process and you can carry out the decarburation at a very faster rate. At that time, from the side also you start the bath by argon as well as oxygen is also there. Okay. So as decarburation proceeds, slowly you reduce this oxygen purging from the oxygen lancing from the top, but you argon purging you go on increasing. Total overall oxygen purging from the top as well as through this nozzle also, through this side lens also, you decrease the oxygen percentage because decarburation, and then you increase the argon purging because mixing is very much important. And post combustion of CO, here whatever the CO will come up, that is be burned under this oxygen atmosphere, and then that will generate the heat. Two advantages there, it will generate the heat as well as you reduce the toxic CO gas emission. And towards the end of the process, you add some ferrosilicon, which is very good because end of the process the temperature of the bath also get increased because of lot of oxidation process. So as a result it goes to 700 degrees centigrade also. You have to use some coolant. You use the ferrosilicon. The ferrosilicon has two purposes. One is that it acts as a coolant as well as it helps in reverting back some of the chromium that was there in the slag. Okay. So that you can do that. And if extra low sulfur steel is required, then again you can take out this oxidizing slag and then you can make a reducing slag, and under the argon starting you can carry out some desulphurization also. Okay, so this is the process, that is the stainless steel making in the EAF AOD route. And okay, now this is the your reference and conclusion. We can say there is the effective desulphurization can be carried out in ladle using synthetic slag, but as I said, synthetic slag is very good, thermodynamically is good, but really if you want to lower down the sulfur to a very low level around 20 ppm also, in that case your starting the bath is very important. You have to start the bath beyond the critical gas velocity where significant emulsification of the slag in the metal take place, then only you can carry out significant amount of desulphurization. Second thing is that in the cash process there is a composition adjustment by silk ash argon purging. Here the advantage is that the slag eye, basically whatever is you can carry out a very intense starting here, and the slag eye is enclosed in a snorkel, such that the slag eye do not have any interaction with the atmosphere as well as the slag, and all the addition is made through the snorkel, and such that and all the addition can be done without any interaction in the slag and atmosphere, at the same time at a very high intense stirring. So that basically increases the melting efficiency and the yield of deoxidizer as well as the alloying element. And finally, the EAF AOD process, that is mostly used for making the global stainless steel. Stainless steel making, that is your EAF AOD process is used. More than 70% of the world stainless steel production take place by the EAF AOD route. And advantage here, the principles is argon basically dilutes the CO gas and reduces its partial pressure, and allows the preferential removal of carbon over chromium. That is the main thing in the stainless steel process, stainless steel making, because first you make the high carbon, chromium and nickel melt in the electric arc furnace from the chief raw material. You produce that thing and then you preferentially remove the carbon over chromium. such that you can keep the chromium in the bath, but you can allow the carbon to go away. So that is the idea, and the AOD process, there is the argon serve that purpose. Okay, and that's all. Thank you very much.